Today we will be talking about more on iterative methods, particularly multigrid, and if we have time, extending these iterative methods to nonlinear problems. So we'll start off the convergence rate analysis we were ending in last lecture. And let's start by demonstrating the convergence rate of Gauss-Seidel. And the last time we did Jacobi for a one-dimensional problem. So this time let's do Gauss-Seidel for a two-dimensional problem. And the two-dimensional problem, let's actually see. I want to try with a image because it's two dimensions. So I have an image. Let's see. Open outside MATLAB is this picture, right? So two airplanes, F-35s. And let's try to see if we can construct a linear problem, like a PDE, where we know this is actually the exact solution, okay? And then this is like the method of manufacture solution. Let's say this is our exact solution and see how fast our iterative method would converge for that. And if you take a look at the image is pretty large. So open folder outside of MATLAB. It's a, where actually do you see that? Oh, maybe let me just show it in MATLAB. It's an image of properties. Anyway, so let's go into MATLAB. It's a 4095 by 4095 pixels. And if you think of this as grid points, it's about 16 million grid points. It's kind of a representative simulation if you look at what's being done right now. Okay, there are much bigger simulations that are run on the supercomputers as kind of the frontier demonstration problems. But if you go to industry, this is the kind of simulations around 1 million to like 100 million grid points. That's the kind of simulations people are running every day. Okay, so let's import this image. Import data. Yeah, it shows up over here. It's the size of this is 4000 by 4000 by 3 because red, green, blue are the three different data. So now it's imported and we have a F-35. Okay, so clearly this is made for a finite difference demonstration because the number of grid points is constructed to be just one less than 4096, which is a proper power of 2, right? So let's first make a solution. Now include the boundary grid points, and we'll set the Dirichlet boundary conditions so that they are 0. So x would be zeros with 4097, right? So that'll be including the boundary grid points. And now let's set the interior. Actually, this x is, we want to be our exact solution, x exact. Let's set it to be like that. And x exact, 2 to n minus 1, 2 to n minus 1. We'll set it to the F-35. Let's just set it to be the first channel, which I think is red. All right. So now we have it. And the problem is when we change this after the colors in the image range from 0 to 255, and we want to, in order for MATLAB to show it, we want to divide it by the maximum number. So the range is 0 to 1. Okay, so let's divide it by maximum of x exact. Actually, we'll just do 255. And if you do IMShow, which is showing a image, it says the image is too large, but like it's scaled it anyway. This is the red channel of this picture. So that's our exact solution. Okay. So now let's think of, we want this to be an exact solution of a Poisson's equation. What is the right-hand side? Well, the Poisson's equation is the Laplacian of x is equal to b, right? So of course the right-hand side should be the Laplacian of x. So let's construct the right-hand side as a Laplacian of x. So B is going to be the same sized array, while the boundaries will not be used. We'll just use the interior. And let's write a code for computing what is the Laplacian, right? So okay, so let's actually write a new code function for Laplacian of x. All right, so the output is going to be b, the input is going to be x. So what we'll do is, first of all, we'll infer the grid points, number of grid points. N is going to be equal to the size of x in the first dimension, actually -1, right? Because the x is actually the number of grid points including the boundaries. Our n, number of intervals, is the size -1. And dx would be 1 divided by n. So we assume it's a square domain with a regular, with spacing being the same in the x and y direction. So the Laplacian would be, okay, so let me say b is equal to the zeros of the same size of x. And the iterate, that's from 2 to n, j from 2 to n, because we are only iterating through the non-boundary grid points. So we'll say b of ij is going to be equal to now the Laplacian, right, in 2 dimensions. It'll be x of I minus 1j, xi plus 1j, xij minus 1, and xij plus 1, right? And then we'll minus 4 times, because we have a Laplacian in the x direction, one in the y direction, both has a 2, so we're having 4 times x of ij divided by dx squared. That's going to be our Laplacian, right? Okay, so let's try it. We said b, okay, this is actually redundant. Laplacian of x exact. Looks like it works, right? It actually takes a non-negligible time to compute it. And if you show the b as an image, it's not really anything you can, it's not very nice.